Okay, so because we are in a big hurry and in a big delay, I decided to help the organizers and skip some of my introductory slides and jump into the deep water right away. So I'm talking about a simulation of boson sampling. Okay, the main problem is here is that you have an optical interferometer made of linear optical element, and we can describe it by unitary U, and you have some input port and output port. These are called optical modes, and on each optical mode you might have one, two, or three photons, and the question is that if you have some input configuration of input photons, what is the probability to detect, for example, one photon on T1 output, three photon on T2 output, and so on. And because you have a superposition and entanglement in your quantum system, the output varies from measurement to measurement, and in the end you would have probability distribution for the possible output state. And it turns out that the probability of one output state can be computed by a so-called permanent of this matrix U. Okay, the basic definition for this permanent is given by this formula. Okay, it's very similar to the calculation of determinant. Instead, you don't have here that alternating -1 factor, which enables you to use theorems from linear algebra to compute the determinant. To compute the permanent, you can do such thing, and it turns out that the complexity of the calculation to calculate the permanent would always scale exponentially with the problem size, even if you use very hard mathematics behind the problem. And here at the bottom is are shown the most powerful mathematical approaches to calculate the permanent. There are two independent formulas, the riser formula and the BB per FG formula. These are the initial letters of four people. Okay, these expression scales with n on the square times 2 on the end, because you see you need to sum up n elements in each rows of the matrix. If we look at this bottom formula, and then you need to calculate the product of these n sums, this gives the n square component in the complexity, and you need to sum up over exponentially large set of these quantities. So this gives the exponential component in the in this complexity factor. This complexity, however, can be further reduced if we organize the sum in a proper way. Namely, for example, if we organize it in a gray code order, which is a sequence of number where only one bit is changed compared to the next number, and this gives you the possibility to reduce previous result. In this case, you can see that you don't need to calculate the whole sum in the expression. You just need to subtract or add a number to the previous sum, and that is the way you can reduce your complexity by a factor of n. We implemented this expression in our Picasso bosonic quantum computer simulation framework. And to be more precise, we didn't implement it, this specific gray code implementation. We have another implementation which basically do the spawning of computation task in a very well designed way. So we don't do this extra logic of gray code indexing and processing. So we are sparing it. And we are comparing our implementation to the Strawberry Fields quantum computer simulation tool, which is developed by a Canadian startup called Xanadu. And here are our results. Okay, the way we are getting rid of that extra logic of gray code ordering, we could achieve 4 times speed up on our CPU implementation compared to the Strawberry Fields. The Varus package is a component of the Strawberry Fields, and we did this benchmark on a very traditional CPU, which is accessible in every supercomputing cluster. It's a very traditional hardware. We run the code on 24 threads, and we also compared our benchmark to the benchmark done by a Chinese group on the Tiahne 2 supercomputer, which was the fastest computer 8 years ago. So this is an 8-year-old hardware, but still, if you know how to use its resources, it is still a very powerful thing. It has 16,000 computing nodes, but this red lines corresponds to the result gain or got only from a single computing node. This is why it's so small line. You see that we are pretty close to it. If you look at the speed up, it's faster than our, but you can say, okay, we can use more hardware and we can be better than their implementation. In fact, they use this n-squared expression to implement on their hardware, and the reason behind that is that it's much more scalable. The catch is that our well optimized or highly optimized CPU implementation is not that much scalable than this n-square implementation of the Chinese group. We are good on shared memory model architecture, but our implementation doesn't scale very good if we are connecting machines in distributed memory configuration. We can scale up to 10 computing nodes efficiently, but not to 16,000 computing nodes. And that made us to think, how can we beat this Chinese benchmark with a scalable solution? That's the point where FPGA-based data flow engine comes into the game. Basically, we are talking about programmable chips consisting of many programmable logic gates, memory units for arithmetic operation, and so on. And the purpose of such hardware is to prototyping application-specific integrated circuits. Many giants use such technique to develop integrated circuits, just like Intel or IBM. And we raise the question whether such an architecture can be used to design ASICs for quantum computing. Okay, this was our question, and we started to look around in the world what kind of solution we can have, and at some point we came into touch with Maxeller Technologies, and from this viewpoint, okay, from my viewpoint, programming an FPGA is something like to have a very complicated structure of pipelines and having data streams moving around these pipelines. And if you need to make arithmetic operation between data that are moving along different pipelines, you need to assure that these data fragments are in the same place and in the same time. Okay, so you are not programming just in time, but you need to consider also the programming in space. And I liked very much the solution of Maxer Technologies doing that. The reason behind this is that we are doing very similar things on CPU, just we call it task flow. And of course on CPU, we have an abstraction. So that task flow is abstraction, and then FPGA we have static data flow. But I like their solution from the start very much. And here is our implementation to calculate the permanent on these data flow engines. So here in the top is the expression we implemented, and the basic idea is that we have this red rectangled part of this expression, and we try to implement it so it can be calculated in each clock cycle tick. So we calculate an addend to the permanent and each clock cycle tick, and also we are summing up these addends, and in the end the data flow engine just return the calculated permanent. The last thing that this last division we are doing on CPU, but it doesn't matter really. Okay, the first step is to upload our matrix onto the FPGA chip. And if you look at an FPGA architecture, the units that you can use to your code are organized in columns depending on their type. For example, okay, we have on-chip memory organized in columns, and we spread the elements of our matrix across the chip to give opportunity to form computational logic around these matrix elements, because we need to decide their sign, we need to sum them up, and so on. In the second step, okay, on the second step, we create a counter for delta. Okay, each bit of this number, which is increasing from 1 to 2 on the power of n, each bit of these numbers corresponds to one element in the delta vector. So for example, to delta j. And we need to get these delta j signs to specific elements of the matrix. This step consumes a tremendously large amount of logic on the chip, and this is the point we are still working with the Maxer to reduce the consumed logic over the FPGA chip. But this currently we have this implementation, and we calculate the sum of this delta times a product for each row j, no, not j, but I for each row of the matrix, which is indexed by I. In the third step, then we need to calculate the product of these calculated sums. And okay, this is the point where these DSP elements comes into the play. They are used to multiplicate the numbers, and in step 4 we sum up these addends, and finally we return the result to the CPU. This is the area usage of the actual area usage of our implementation. This is one FPGA chip, which is divided into 4 distinct blocks. There are wiring between these individual blocks, but it's much harder to pass data from one block to another than pass data between elements in a single block. So you need to keep it in mind when you design your implementation. And here each color represents a different kernel. This kernel implements these steps I was just showing you in the previous slide. Okay, the things are much more complicated, but I don't want to go into details. The fact is that we have now 72% of utilization of the resources on the FPGA, and we are trying to reduce mainly the logic, because we see from the numbers that the logic is the bottleneck in this implementation. We are trying to use that gray code ordering with the software engineer from Maxeller. So this is we are working on currently. Now let me show how we can compare the performance to the previous benchmark. We see that okay, in fact, it turned out that for larger matrices we can't fit our implementation on a single FPGA chip. So we decided to connect to spread the implementation over two FPGA cards and have a connection between them, which allow us to transfer 35 gigabits in a second. And this implementation gave us a further improvement in performance. Practically, we are 2 times faster than that benchmark on Tiane 2 supercomputer. Okay, but you can ask that it's an old hardware. You could probably do the same speed up with a modern GPU, and that's right. You can do it, but you can't do it one particular thing with GPU. Namely, we are doing arithmetic on 128-bit number representation. Typically, CPU and GPU hardware have 64-bit arithmetic unit, and doing higher precision calculation, you would need to use software solution. You don't have hardware support for that. And when you start to do it on CPU, on GPU, you are starting to lose performance. So this is the point where FPGA-based data flow engine have an advantage over GPU technology. And it turns out that in quantum computing, there are many such matrix functions where you need to have such precision. Here is an analysis of that Chinese group, estimating the error of the individual implementations. Here we see the red line correspond to the riser formula, and the red one to the Glean formula, and that's the reason we started to implement the Glean formula, because it's much more stable. Here they estimate. Here they calculated the error because they did the calculation in a very specific matrix which has entries once in each place, and it is analytically easy to calculate the permanent. In boson sampling, you need to process unitary matrices where A is a unitary, so it's a little bit different. But it turns out that in practical situation, this error it's increasing. Basically, you start with a matrix with elements 1 over square of 40, and you end up with a permanent of a value 10 on a minus 12. Okay, for this calculation, basically the double precision is not enough. You need long, extended precision on CPU on GPU, and in our implementation we have that precision. But 128-bit number representation is a little bit too much. It's more just like a demonstration that we can do it, because even if it's not necessary to use that high precision to calculate the permanent, but there are many other matrix function that, on the other hand, would need such a precision. For example, to calculate the Torontonian, it has been shown that 128 bit, it's not enough. You need 258 bit to represent the matrix and obtain a result that can be trusted. Okay, so basically this was my talk. This was my conclusion that I think quantum computing might benefit from data flow engines a lot. We just started to work on some project. This is our first result, and I think that this is the first time that someone can show that FPGA can be used to calculate some useful quantities in quantum computing. Okay, so if you have some question, I am here to answer them. Thank you for your attention, and that's all from my side.
Thank you very much, Peter. It was a very compact and nice talk, and I'm very happy that we are already in the situation that these technologies can be used in the Quantum Information National Laboratory. I'm asking the audience whether we have a quick questions or remarks related to this one. I think many people here would like to jump on the coffee.
Okay.
Here, so it was a bit of thing. So I think can you stay with us for the rest of the?
I have a question.
Please.
Okay, go ahead.
I have a question. Don't use that, please. Speak up because it's echoing.
So the A matrix is a square matrix in all cases.
Okay, I would ask someone to repeat.
I will repeat the question.
Okay.
So the question is something that whether the A matrix is a n by n matrix.
Yes, that's right.
Yeah.
Okay, we have an implementation that can be used to arbitrary size. There is a trick in it. So we don't need to have an implementation for each size n. I don't want to go into details, but there is a very simple and very nice trick to do it on a static data flow engine.
Mm-hmm.
For the may I ask about what's the D vector?
Yes.
Okay. I heard the D vector, or I don't know.
What was the D vector? That's the question. So what was the D vector? That's
okay. The D vector is an auxiliary variable. It is a vector with elements -1 and 1, and you need to iterate this red rectangle over each possible set of these -1 and 1 values. So this is a delta vector.
Wait.
Okay. Thank you very much.
Okay. Thank you very much, Peter. So
okay, you are welcome.
Thank you.